Now let's take a look at the first derivative test. So the idea is that we can use the f prime x to find the extreme values. We call f prime x the first derivative of function f. Okay, so here's a review of the definition of the derivative. So the derivative of function f at the point x is a limit when h is close to 0, and the change of the function f over the h. So let's look at two graphs to show why f prime x can be used to determine the maximum and minimum value. So here, in the first graph, we assume that h is a large and positive number. And so we don't take the limit. We just assume h is some constant positive number, right? So this thing is called the average rate of change. Because h is some positive number, for example, h equals to 2, right? And the change of the function value in the h period, in the h interval, is called the average rate of change. So let's see. So when h equals to 2, for example, suppose we want to find out the average rate of change of the function from x0 to x0 plus h. The way we do this is to first calculate f x0 plus h, which is this point, and then calculate f x0, which is our original point here. So from here to here, the interval here, or the distance here, is the change of the function f. Right, so this distance is f x0 plus h minus f x0. It shows the change of the function f from x0 to x0 plus h. And if we divide the distance, or divide the difference between these two over h, so this is the average rate of change in this interval of the function. And this thing, the value of this equation is just the slope of the segment here, the slope of this line. Okay, so now if we take the limit of h, so that h equals or close to 0, right? Suppose h changes from 2 to 1, right? Becomes a relatively smaller positive number. So if we draw the graph again, it should be somewhere here, right? Because h is half the original value. And so here, this should be x0 plus h over 2, for example. And then the segment, we call the segment, becomes here, right? It's closer to the curve. And if h is even smaller, right? The smaller the h, the closer the second point, f x0 plus h, will be closer to f x0, right? So at first, f x0 plus h is here, and then you move down to here, and if h becomes smaller, it becomes here, right? The 2 points becomes closer and closer. And if we draw the line between them, the line will be closer and closer to the curve. So in the extreme value, when h is very, very close to 0, it's very close to 0. So the 2 points are very, very close to each other. And if we draw a line between them, the line is just like this, right? We call this the tangent line because there's only one intersection between the curve and the line, which is the point x0, right? Because the 2 points f(x0) plus h, and f(x0) becomes like overlapping to one single point when h is close to 0, right? Take the limit. So if we draw a line between the 2 points, they're very, very close to each other. So this line is called a tangent line. And this value, we call this instantaneous rate of change. It's not average rate of change, it's called instantaneous rate of change at the point x0. This is because we take the limit, right? When h is super small, then the change of this point is just the instantaneous rate of change. Okay, and this is just a definition of derivative. And this is also the slope of this tangent line. So here, this value is the slope of the segment here. And here, for the second case, the limit of this value is the slope of the tangent line. So that's why we can use the slope of the tangent line to show whether or not this is maximum or minimum. I'll show you that later on. So here for these two examples, I just want to show you that the derivative is closely related to the slope of the tangent line. So if the slope is positive, like in this case, the slope is positive, so the derivative is also positive, right? Because the change is positive. Look at here. So the average rate of change in this case is positive, right? Because fxh plus h is larger than f(x0). So this value is a positive number. So if you take the limit, h is still a positive number, but it's super, super small and relative and very close to 0. But again, f(x0) plus h, although it's very close to f(x0), but it's still a positive, but it's still larger than f(x0). So this number is still a positive, although it's super, super small, right? So when the slope is positive, also the derivative is positive. And when slope is negative, then the derivative is also negative, right? So here we take the derivative, we take the slope of the other tangent line here. So the derivative is also negative here, right? You can think of the process like climbing the mountain, right? So when the slope is positive, the curve looks like this. It looks like this, right? It's climbing with increasing function, right? Because the change of fx or the change of y is a positive number. When the change of y is positive, and so the derivative is positive, and so the slope of the tangent line is positive, right? But if the slope or if the curve is like downward sloping, or the curve is like decreasing all the time, and also the derivative should be negative, and also the slope is negative, right? Because the change of y from point 1 to point 2 is a negative number. And based on the definition of the derivative should be negative. And also the slope of the tangent line is also negative, right? Because this is a limit of this small change. So here we have our first derivative test for the relative extreme. We have 3 cases, and each of them can be identified by the first derivative. So if the first derivative of a function f(x) at x equals to x0 is that f prime x0 equals to 0, right? So the slope and the derivative at point x0 is just 0. If this is the case, then the value of the function at x0, which is fx0, will be, there are 3 cases. The first one will be a relative maximum if the derivative changes its sign from positive to negative from the immediate left of the point x0 to its immediate right. Okay, so what does it mean? I draw a graph here. So in this curve, the point D is a relative maximum, right? Because all the points, all the nearby points in the left of D, the value of the function is smaller than D. And if x is larger than D, then fx is smaller than fd, right? So it's like the peak of a mountain here. So D is a relative maximum. So we can see from this graph that for the nearby points, the smaller than D, right? For example, in this period, in this interval, right? The nearby points. We don't look at the point here in the C here. We just look at the nearby points. So in the points that's immediate left to the point D, because we're climbing the mountain, so the rate of change of f, remember the rate of change is f x plus h minus f x, fx, and then divided by h, right? Because this is an increasing function to the left of the D. So when x increases, fx also increases. So the rate of change is a positive number. And if we take the limit, we can get the derivative, right? So this is a rate of change. And if we take the derivative, if we take the limit, then we can get the derivative. But the signs of the two should be the same, right? Because here h is a larger positive number. And here h is very close to 0, but still a positive number. So even though this is the average rate, this is the instantaneous rate, the signs should be the same, right? So because it's an increasing function in this little interval here, so the average rate of change and the instantaneous rate of change are positive, right? So based on the definition of derivative, the derivative in this interval is positive. So that also means that if we draw a tangent line to any of the points in the interval, right? For any of the points in the left neighborhood of the point D here, for any of the point in this small interval, the tangent line should have positive slope, right? Because to the left of D, the function is increasing. So the slope should be a positive number. And similarly to the right of the point D, because the function is decreasing, right? For x that's larger than x0, when x increases, fx decreases, right? So the average rate of change or the instantaneous rate of change for the function y, for the function f, from here to here, for example, is negative, right? It's negative. So the derivative in this interval is negative. And also the slope of the function is negative. If we draw the tangent line here, there should be downward sloping, right? It's a negative number. So only when it reaches a peak, for example, only when you take the derivative at point D, the peak of the mountain, only in this case, the slope of the tangent line equals to 0. Right, we call this stationary point because in the relative maximum point here, neither the slope is a positive or negative number, right? Because it's reaching the peak of the mountain. So everything to the left has positive slope. Everything to the right, it has negative slope. So here we're just talking about the relative, the immediate neighborhood of the point D. We're not talking about the point C here. We're just talking about in a small neighborhood to the left and to the right of D. Right? For the left neighborhood, the slope is increasing, or the slope is a positive number, right? And to the right, it's a negative number. So in the middle, it has to be 0, right? So when f prime x equals to 0, it may indicate that this point is a relative maximum. And for the second case, if f(x0) equals to 0, f prime x0 equals to 0, it may also indicate that it's a relative minimum if the derivative changes its sign from negative to positive from the immediate left to the immediate right. So we can look at here the point C, right? From this graph, we can see that the point C is a relative minimum, right? Because it's a trough in the curve. So for the immediate left of the point C, look at here, it's a decreasing function, right? So for decreasing function, we know that the slope is negative all the time. No matter what point you choose in this small interval, the slope of the tangent line should be negative, right? And for the immediate neighborhood to the right of the C, it's an increasing function. So for all the points in this small interval, if you draw the tangent line, the slope is positive, right? So for all the points to the left of the C, not all the points, to the points in the small interval that's left of C, the slope is negative, and for the right, the slope becomes positive. So there has to be a point where the slope is 0, right? Because the slope transitions from negative to positive. So there has to be somewhere in the middle where the slope is 0. And that point is point C, which is the minimum, the relative minimum of this function. So when the slope equals to, or when the derivative equals to 0, may also indicate that this is a relative minimum. Okay. And for the third case, it may neither be a relative maximum nor a relative minimum, right? If the derivative has the same sign on both the immediate left and the immediate right of point x0. So here we have the case C here for the second graph. Right, so look at the point E. Point E. To the left of point E, the slope is positive. Right, the slope is positive, and to the right of E, the slope is also positive. But at the point E, the slope equals to 0. Right? So this is like when you draw the slope of the tangent line, little by little, you can find that, okay, at first, the slope is very large, right? The slope is very large, or somewhere here, the slope is like this, right? The slope is a very large positive number. And then it becomes flatter, and then flatter, and then becomes flatter again, right? So each time you increase the x little by little, the slope of the tangent line becomes flatter and flatter until it reaches the point E, where the slope becomes 0, right? Just a flat straight line that's parallel to the x-axis. And then to the right of the E, when x is larger than E, the slope becomes positive again. It becomes very flat but positive, right? And then when you increase the x a lot, the slope becomes more and more positive, right? It becomes a very steep upward sloping line. So in this case, from this graph, we can see that the point E is not a maximum or not a minimum, right? It's not a peak and it's not a trough for the curve. But the slope of the point E equals to 0, right? So in this case, point E is not maximum and not minimum. So we have to exclude this case when we are finding the relative minimum and relative maximum of the curve, right? Okay. So I'll use an example to show you how to find the exact minimum and exact maximum for the curve. So here we talk about the 3 cases. So I'll show you the example of how to differentiate whether or not the point where the slope is 0 is actually a maximum or minimum or neither. Right. So the example is like this. Find the relative extreme of the function, this thing. Right, it's a little bit complicated. Okay, so we said that we can use the first derivative to find the relative extreme, right? So the first step is to find the derivative function. So I take the derivative of this function, and we can get f prime x equals to this thing. Okay. And then our goal is to find the point where f prime x equals to 0. Right? And then we test whether or not it's a maximum or minimum or neither, right? So we need to find the result. So we need to find the values of x that satisfy this equation. So the f prime x is just this equation, right? We let this equals to 0. So this becomes a quadratic function. So we need to find the 2 roots of this function, right? Because it's a square of 2. It's just a second order, right? The highest order is 2. And so if it's a quadratic function, the highest order is 2. And so we typically have 2 roots. So we use a quadratic formula to find out, okay, there are 2 roots. One is 6, one is 2. So the third step, which may take a lot of time, is to determine whether each of the stationary values is a relative maximum or relative minimum or neither. So the way we test this is to find the immediate neighborhood of the root. So for example, when x equals to 6, and we find the immediate neighborhood of x equals to 6. So for example, we can plug in x equals to 5.9, right, to this equation. You plug in x equals to 5.9 to this quadratic function. right? Because the quadratic function is the first derivative, right? It's a derivative function. And you see whether or not f prime x is a positive number or a negative number, right? So in this equation, in this example, for x is smaller than 6, but it's in the immediate neighborhood of 6. So for example, x equals to 5.9. So when x equals to f5.9, you plug in this first derivative function, and you find that f prime x is smaller than 0, or it's negative. And for x is larger than 6, for example, you can try x equals to 6.1, right? That's the immediate neighborhood to the right of 6. And then you can find that, okay, the derivative becomes a positive number. So, sorry. So for the to the left of 6, the slope is a negative number, so it's downward sloping curve, right? To the right of 6, the slope becomes positive again. So to the right of the 6, the slope becomes positive. So this is an increasing function again. So that means that x equals to 6 is a relative minimum, right? And for the immediate neighborhood of x equals to 2, for x smaller than 2, you can plug in, for example, 1.9, right? To this quadratic function, to the first derivative here. And you'll find that f prime x is a positive number. And for the immediate right of x equals to 2, for example, x equals to 2.1, you plug in the first derivative function and find that it's negative. So that means that f2 is a relative maximum, right? So for the neighborhood that's smaller than 2, the slope is positive. So it's an increasing function. And for the points that's larger than 2, the slope becomes negative. So it's a decreasing function. So 2 is a relative maximum here. And if we draw the graph of this function, you'll see that it should be something like this, right? 2 is a maximum, relative maximum, and 6 is a relative minimum, right? So suppose we again calculate the immediate neighborhood of the root. We find that when x is smaller than root, or x is larger than the root, the signs are the same. For example, f prime x is positive for the first case, and it's also positive for the second case, or negative for the first case and negative for the second case. The signs don't change from the left to the right. So if this is the case, then it means that the root is false, or the root doesn't mean anything, or it's not a maximum and it's not a minimum for this root, right? So we have to exclude that to our answer, because that root doesn't mean we have a maximum and relative minimum, right? So this is a way how we find the relative maximum and maximum minimum, by taking the first derivative of the function and find out the roots where f prime x equals to 0. And then we test the immediate neighborhood of the root. We test the signs of the first derivative, and to see if the sign changes, right? So if the sign changes from negative to positive, then this is a minimum. And if it changes from positive to negative, so this is a maximum, right? So that's how we do this.